let's start with something that I view to be pretty easy. Talk about the two vocabulary words that we use to describe things that are spinning. What are those? I'll give you a hint. They both start with an R.
Radians?
Ah, I didn't think of that one. That's part of the parts. Let's say that that's integral to things spinning, because they always are going to spin with some kind of radius that you have to define. But what are the actual words that describe the spinning itself? Revolution is one, and the other one, I'll give you another hint, is on the board.
Rotational.
Rotation, right? So,
There's two R's on there.
this is good. Yeah. Rotation and revolution. So let's get some working vocabulary out in the open. Are those the same word? They're not, are they? So what's the difference? Who can help me out? What's the difference between a rotation and revolution?
Isn't rotation just in place while revolution is going around?
Well, how can you be just in place? What do you mean?
Well, like spinning around, but you don't move.
On top.
Yeah.
A top. So the object can't be moving?
Yeah.
Okay. What if I throw a perfect spiral with my football as I pass it to you? Is the football then doing revolutions? Or is it rotating? It's rotating, but you just said I have to be sitting still. Football's moving. You're really close, but the movement part troubles me, right? Because I just gave you an example of rotation when something's moving. So what's the difference between the two? What axis? So, and which one are you talking about? Rotation is spinning about an internal axis. That's what you were trying to get at, right? An axis that's going through you. So if I am spinning on my ice skates, I am making a spinning motion about an internal axis that's going through me. Now, let's go back to the football example. I throw the football with a perfect spiral, and the axis, we know, goes between the points of the ball. Now, if the punter punts the ball, and it goes end over end over end over end like that, is that still rotation? The answer is yes. But instead of the axis going through from point to point, it's going through the fat part of the ball. It's still rotation, right? It's still about an internal axis. Regardless of what direction you spin it, you can spin it in any crazy way you want. It's still rotation. Revolution is when you are spinning about an external axis. So you're going around something. Like, for example, the Earth. We are revolving, and, well, let's do one at a time. We are revolving around the sun. And that creates what we refer to as what? Years. Right? That puts years on us, right? So we're going around the sun, that's making years. We are rotating about an internal axis, and what does that make? That makes days, right? So the Earth is doing both things at the same time. It's spinning about an internal axis that we call its axis of rotation, and it's revolving around an external axis that we know changes our seasons and does all of that other stuff, right? Okay, so what we're going to talk about in this chapter is a bunch of rotational stuff. Now, what does that mean? That means that we're going to be talking about how things spin about an internal axis, right? And in order to do that intelligently, we need to talk about some stuff that I hope you already know. Now, what is it that I'm hoping you already know? The most important thing is this guy, right? What's a radian? How did you learn this definition as a sophomore? Probably again as a junior. But it still seems like a mystery to a lot of people. What's a radian? How did we, so let's start with the definition. How would we define it? Or what do you want to define it in terms of? I don't know what that means. It's part of a circle. I like that. what we're trying to do is, so we're saying it's part of a circle, we're trying to figure out what part of a circle it is. And Alex is right on top of it. Just needs to define what that arc length needs to be in order to understand what a radian is accurately. What arc length specifically do we use to define a radian?
The one equal to the thingy that radius.
Yes. If you take an arc length, the distance along the circle equal to the radius of the circle, the angle that you deflect is 1 radian. I can't believe how many of my students at a high level, all the way in calculus, forget what it is they're even talking about. So let's go over it again, one more time. Now, here's my object that's going to go around in this circle, okay? As it deflects, where this length r, I translate on the outside of the circle like that. If this distance r is the same as this one here, the angle that you deflect in moving from our reference axis that I have in red up to the new point is an angle of 1 radian. Which is what I put down there. If the point travels along the outside of the circle for a distance equal to the radius, the angle covered is equal to 1 radian. That's the definition of a radian. So, let's talk about some other ways that we tend to measure things. What if I make my arc length the entire circumference? What would I say then? What is S?
Well, the whole thing is 2 pi r divided by r times 6.
I don't know what that means.
Well, the equation for circumference of a circle is 2r.
Thank you. Stop. Okay, so the circumference is 2 pi r, and now I'm going to make that the arc length. So if I put that in terms of what we just learned and make my substitution, what's the circumference, or the whole circle, in terms of radians? Say it louder.
2 pi radians.
It's 2 pi radians, right? So one time around, one revolution around for that object is going to be equal to 2 pi radians. So what we are trying to establish today is how to talk about things as they're spinning in terms of this kind of tough to understand unit of radians. Radians are, we can relate it to degrees, we can relate radians to circumference, we can relate radians to, in other words, distance around a circle, we can relate radians to revolutions, the number of times you went around, right? Any of those. It's just going to become simple factor label. That's what we're going to figure out today. So let's talk a little bit about that. So the angle that you deflect when your arc length is equal to the radius is 1 radian. That's what we just said. And therefore, 2 pi radians equals 360 degrees. So if I give you degrees, right? If I give you degrees, you can figure out the radians. If I give you radians and you want to, you can also go back and figure out degrees. You can go back and forth. Ultimately, the factor label that I was talking about just a couple minutes ago is this one. The 2 pi radians equals 360, which equals 1 revolution. So if I give you revolutions per second, you can make it radians per second. If I give you the number of degrees that you deflected in any given amount of time, you can do the same thing. So as you watch this thing spin, let me slow down. So as you watch this thing spin around, the angle that it's deflecting from its reference point, so it starts here, as it goes around, the angle that it's changing, the amount that it's changing, is going to be what we're going to measure as the displacement of this reference line. So as it sweeps around in the circle, the displacement that we're going to measure is going to be in radians. It's not going to be in revolutions, and it's not going to be in rotations or in degrees. It's going to be in radians, which is not a big deal because we know how to relate from one to the other to the other. Now, what I want you guys to get in your head is we already learned how to describe motion once. We did it the easy way at the beginning of the school year because it was your first physics experience, right? So we talked about motion in a straight line. What you're going to learn today is motion in a circle for things that are moving. When we describe it in terms of the angle, is the exact same in terms of the relationships, the equations. What's the relationship between displacement, velocity, and acceleration when we are dealing with a circle? Well, they're very, very similar. So we talk about the angular displacement. The object starts here. Basically, this line here is our reference line as it goes and sweeps through. The angle that it sweeps through is what we would refer to as the angular displacement. So if this thing moved from here all the way to here, the angular displacement would be whatever radians you have traveled through. How much is 1 radian in degrees? Does anyone know?
57.
Exactly 57, right? What are you, I mean, you could go and do that 2 pi, that 360 thing that I was talking about before, and you could figure it out exactly, right? It's about 57 degrees. So, as you sweep around the circle, you can figure out exactly where you are if I tell you what that angle is in radians, right? So that's where you are. What do we call that when we were dealing with linear motion? That's your position, right? Your position in circular, in rotational motion, is going to be theta. So we're going to describe where you are in the circle based on that angle, right? That's this, angular displacement. Angular velocity is really no different in the way we think about it than how we were able to come to the conclusions about linear velocity. So if where I'm at is going to be described by this angle that I've created as I've gone around my circle, if I know how much time it took for me to have that happen, then I know what my angular velocity is. Angular velocity describes how fast you are changing your position. How much, the rate at which you're changing your position is your angular velocity. So, there's where I'm changing my position. The rate always implies having time in the denominator. So the rate at which you change your position is just going to be the change in the angle divided by how long it took for that to happen. So the units have to be position units, radians, divided by time units, seconds. So when I see radians per second, I'm already thinking about this. What's this? Does anybody know what that stands for? That's omega, right? And why would we not just use V here? It's already taken, right? We're going to make a direct correlation between velocity, acceleration, and displacement, but all 3 of the ones that we use for rotation are all Greek letters. So omega, you can think of it as like the Greek letter for V, is going to be what we're going to use for velocity of things that are spinning, because we've already used V for translational or linear motion of something that's moving, right? We don't want to get confused. So in order to not confuse things, we just change the variable altogether, but you're going to see that there's a lot of similarities. So far so good? So if I'm sweeping from here to here, and I know how long it takes for that to happen, not only do I know what my new position is, I also know what my angular velocity had to be. It's just going to be that change in angle divided by time. Okay, now, here's where things get a little more complicated. Now this thing has a small amount of friction, so as I spin it, it will take, just at this speed, it would take a long time to, for there to be any evidence that it's slowing down at all. But it is slowing down a little bit at a time, and if I put my finger in the bag to kind of increase that a little bit, what are we seeing now as far as the sweep of that angle? What are we seeing?
Deceleration.
We're seeing deceleration, right? So, just like what we did with linear motion or kinematics in one dimension, when we were talking about V equals d over t, for example, we knew that that was just a limited number of problems that you would use to solve that, right? Things don't go at a uniform or an average speed all the time. There's always got to be a period in time where you speed up, you get to that constant speed, and then you would slow down and then end up stopping, right? So there's always, in whatever motion that you would examine, more than just constant velocity, there's going to be accelerated motion. That's true for things that spin as well. You go to Great America, you get on one of those spinning rides, right? The very first thing that you see, people are sitting down, putting on all their safety stuff, and then what happens? They turn the motors on, you start from an initial turning speed of what? 0, and then you get up to speed. Is there a time when you're undergoing uniform circular motion? Yes, right? Somewhere in the middle. You're going, they got you going at a constant speed for a while in that circle, you're going, and then what happens? They turn the motors off, and then friction takes over, and what do you start doing? You start decelerating until eventually they put the brakes on and you're all the way back to a stop, right? So, what do we use to describe the beginning and the end? Well, we've got to understand something about what happens if it's changing. So if this disc is spinning in this direction like this, at this point in time, I've got an angular velocity of omega initial, and as it slows down, over here I've got an angular velocity of omega final. Then the change in speed divided by time, which is how we defined acceleration in August, the change in v over t was defined as the acceleration. Well, in rotational motion, what's that? A fish? That's alpha, right? And what Greek letter do you think alpha represents? A. And so what do you think that represents? Acceleration, right? So this is the angular acceleration, and it equals the change in angular velocity over the time that it takes for it to happen. You can break that down, right, into final minus initial divided by time. If you do that, so that's where we are right here, right? If you do that, you end up with an equation that looks really similar to one that we already learned before. Because I could put that over here, and then you have something that looks really, really similar to V final equals V initial plus A times T. In fact, it's not really, really similar. They're the same thing. We've substituted some variables, which I'll go over. Does everyone understand the slowing down of the disk? So now my velocity is changing as I go because it's going slower, and that means that I'm going to have my initial is going to be bigger than my final, and so what's my acceleration going to be? If your initial is bigger than your final, what sign do you have for your acceleration? It's going to be negative, right? You're slowing down. So you're going to have a deceleration. So alpha can be positive if the object that's rotating is going faster as it goes, or it could be negative if you are slowing down. And the equation takes care of itself, because you'll know if this one's bigger than this one, then it's going to be negative. If this one's bigger than that one, then it's going to be positive. Make sense? All right. So now let's take a look at some of these similarities. In rotational motion, this is displacement, this is velocity, this is acceleration. In linear motion, we learned that displacement was x if you're going horizontally, or y if you're going vertically, right? So x or y, just based on, trying to keep the symbols similar to what you learned in math. V represented velocity, and A was acceleration. So, Here's the next logical step. Linear motion. These are our equations. I pulled them right off of the AP sheet. Right? You know them all already. We learned them in August. We relearned them in projectile motion to deal with two-dimensional problems, but they were the same equations, right? This is the third time we're revisiting. So this, V final equals V initial plus A times T, turns into omega final equals omega initial plus alpha T. I take all of my V's and I replace them with omegas. I take all of my X's and I replace them with thetas. I take all of my A's and I replace them with alphas, and I get from these equations to these equations. That's where it comes from. So this is just the foundational stuff. I mean, obviously we are not, we're not going to be done with what we need to learn after today, but if you understand what we're doing today, Chapter 8 is not going to be that big of a deal. Let's do a sample problem to make sure that we understand how to use all of the equations. So here's the first sample. If we get through both of them, fine. If not, you're going to have the second one be your homework. And by the way, mentioning homework, I thought that Wiley was sending you guys like a little message when I post something, and apparently it's not working. So here's my message being sent. I have posted Wiley for both energy and for rotational motion. So there are some problems up there for you to practice on. But the one that I'm going to give you is the second one here today. That's going to be priority because that was where we'll start on Monday. And Monday then maybe we'll even have some time to do some wiring in class. I don't know. We'll see. So here's what we got. Passengers on a circular motion ride like the orbit at Great America with a radius of 7 meters make 8 revolutions per minute. Calculate the angular velocity, the centripetal acceleration, and the angular acceleration. Okay. So what are we going to do? Let's start with a picture. Good, I like that. Okay, so this, all right, so there's my picture. It's amazing, I know, right? All right, so there's the picture. And so I'm trying to find the angular velocity. What do we measure angular velocity in again? Radians per second. Okay, so my first thought is this 8 revolutions per minute thing, that's not going to work for me. Right? What do I need to get? Radians and seconds. So here's what I would do. What you guys are going to realize is to get this, all I have to do is some factor labeling. Well, the rest of it's useless in figuring out the angular velocity, you're right. But what's the angular velocity going to be? Well, let's see. It's going to be, if I start with that, then I would just do that 1 minute is what? And then, where am I going to put the revolutions? What am I going to put on top? Now I have what I want. So what does that tell me to do? It's saying take 8, divide it by 60, and multiply by 2 pi. And I've got omega. What's 8 over 60? 0.15, something like that. I don't know. How much? 0.13. So I've got 0.13 times 2 pi 0.13 times 6.28, what do you get?
28.2.
Okay, so that one's done. Yes.
Where did the 2 pi guys come from?
Well, one revolution is one time around the entire circle, right? So how many radians is it? How much is one circle in terms of radians?
I just don't get that calculation.
Well, it's 360 degrees to go around once, right?
I mean, the whole like, you go from I know the whole like turn it into revolutions per second, so that way you get into radians, but I don't know how you can go to revolutions per second to radians.
Well, the seconds they're two separate calculations. I just combined them in one. That's probably what confused me. So the first calculation, the first factor label is that I don't want minutes as my time. I want seconds. So I did that one first. Then I was actually, instead of being in revolutions per minute, I was in revolutions per second. Then from revolutions per second to go into radians per second, I had to make a second calculation, the second factor label, and that's where the other one came in. So don't try to combine them. They are two separate calculations. One was that I didn't have the right time. The other was that I didn't have the right circular measurement, right? So if I go around a circle 8 times, how many radians is that, is the question. Does that make sense? What is it? 16 pi. So you can do that first if you want, but then you're going to be in radians per minute. So you're still going to end up doing the seconds thing, right? Because you got to get to the seconds. So it's my fault. I didn't mean to confuse you by doing it all in one like kind of line, but you can do it that way. That's just the way I learned how to do it. If you want to do them separately, you can do them in either order. You're still going to end up in the same spot that I did. All right. All right. So now, here's the crazy thing. We didn't do anything really with anything new. All we did was factor label, right? That's all it was. But the next question, a little bit more of a challenge. If you want to figure out what the centripetal acceleration is, we did that in chapter 5. There's only one equation that says AC on your AP sheet. It's that. Right? Now, this really is circumference over the period squared, d divided by t, over r. For things that are moving uniformly, which this obviously is. This is a constant velocity problem, isn't it? There's no talk about the wheel speeding up or slowing down at all. So, therefore, we're assuming that it's just going at a constant rate. If it's going at a constant rate, then this is true. So I got to figure out what the period is. Well, if it's going around, if it's making 8 revolutions every 60 seconds, that was given in the problem, right? Does everyone see that the time that it takes to go around once is 60 divided by 8? That's the total time it's going. How many times did it do it? 8. So the time that it takes for it to do it once is 60 divided by 8. Which is what, about 7.5? Something like that? Yeah. So the period is 7.5. The radius is 7. You just plug in. So we know now R and T from 8 revolutions per minute and from the 7 meters, and we can just get the acceleration. The third question is a kind of a trick question. It's asking us for what the angular acceleration is when everything in the problem is telling us to assume there is no acceleration. So what's the angular acceleration if we're going around and the angle that's sweeping is a constant? It's 0. So the answer to that one is just 0. So far, so good? Not too bad? Let's go to one that's a little bit harder. Everybody in here know what a grinding wheel is? that's like one of those things that you use to kind of smooth things out. Sometimes to take some material off of something, right? Some of them have like really, really high friction that they can produce. Others are just designed to polish stuff. But basically it's a wheel that's attached to a motor that spins. So a grinding wheel is initially at rest. We turn it on and we let it rotate for 8 seconds at an acceleration of 5 radians per second squared. Then we turn the power off. The wheel is allowed to coast to rest with a uniform deceleration in 10 revolutions. I want you to determine the acceleration that brings the wheel to a rest. And this is a little bit of a hint there. Right? And I want you to determine how long it's going to take. Does the wording of these problems, it should give you a little comfort. It should feel a little comfortable, right? Have we done problems before where we're asked for how far and how long it takes? And how long? Yeah, we've done a ton of those, right? This is really similar to the kind of stuff that we were doing in linear motion 3 months ago. So I'll repeat the whole problem. Grinding wheel, initially at rest, is allowed to accelerate for 8 seconds at 5 radians per second squared. We turn the power off and we allow it to decelerate through 10 revolutions. Determine the deceleration and the amount of time that it takes for that to happen, for it to come to a complete stop. Okay? We have some time, right? You think we'll get through it?
Yes.
You think so? All right, start working. Everyone following? Did I lose anybody? I may have. Here's why. First of all, does everyone realize that all of this info that I was given at the beginning was to figure out how fast the wheel was spinning when I actually turned the motor off? All of the questions that I asked you about were ones that referred to what was happening after the motor stopped spinning, right? Or after the motor's power went out and it started to slow down. There was no more acceleration, I was decelerating. So in order for me to do the problem, I needed to use the 8 seconds that it was accelerating for to figure out exactly how fast it was going when the power got cut. So then it starts slowing down, but what was it going when it started to slow down? The answer there is it was going 40 radians per second, right? The acceleration of 5 for 8 seconds got it up to 40 radians per second. That's what it was doing. Then it starts slowing down uniformly. So this becomes the V final for the first part, when it was accelerating, becomes my V initial, my omega initial, in the second part. And what's going to end up doing? It's going to end up coming to a stop. How long does it take to stop, distance-wise? I shouldn't say how long, how far. How far does it go before stopping? 10 revolutions, or 20 pi, right? So I just plug that in. So omega final squared equals omega initial squared plus 2 times alpha times delta theta. And then the only thing I don't know is A. So when you solve it, you get that, which 1600 goes into 40. So what do you end up with? 40 over pi? Negative 40 over pi is A. Radians per second squared. And then in the second part, how long does it take for it to stop? Well, now that I've got, and that shouldn't be an A, that should be an alpha, right? Now that I've got alpha, I've got V initial, I've got V final, can I get the time? This term's going to be negative, right, because A is negative. The alpha is negative. So when you plug this in, it's going to be this times time minus half alpha t squared, and then you solve that for t. So now you can just worry about Wiley, because we did the same.